Alright, so we continue on the same theme. Hopefully by now you're starting to believe this statement here. If you can imagine it, if you can imagine yourself cutting things up in infinitely many small differential pieces, the fundamental theorem of calculus will help us solve them. Think about how many things we've cut. We've cut areas into small pieces. We've cut volumes into washers, disks. We've cut work into little pieces of work. We've cut force into little pieces of force, water, everything that you can imagine that you can slice up into small pieces. All of your problems in life, if you can just slice them up into little manageable pieces, the deep S will take care of the rest. Hopefully we've made that point very, very clear. Incredible combination, common sense and fundamental theorem of calculus. These are a dose of common sense for today. Today we take a look at a shape such as this one. This shape is more or less a box shape, and we ask ourselves some common sense questions like, hey, what's the volume of this? Well, let's not suppose it's small. Suppose it's normal shaped. How would you find the volume? And any third grader will tell you the volume for a box like this would be the base times the height times the width, however wide it is. So it's base times height times however wide this is. It's almost the definition of volume. Of course, we take it one step. We add a little twist to it. Literally, we add a twist to it. We take this. What if we twisted it this way and made a circle out of it? Suppose it was thin enough to where it would bend, such as this. Now I ask you, what's the volume? Well, if you don't know how to find the volume of circles like this, just cut it here in the green line and open it and find the volume of that. It's the same thing. Supposing it's thin enough to where it bends, these two would have the same volume. It's just this one, you just add a little twist to it, literally a little twist to it, and you get the volume here. So this one would still be base times height times the width. And of course, the height would still be the same as before, whatever height this was. And there's only one little twist to it here. When you take the base, you twisted it, and it's no longer quote-unquote base. Now it would be the circumference, 2 pi r, where you take the center around where you made the twist, and you measure the radius r here. And you probably want to go towards the middle of the two. And times the height times the width. That would give you the volume. Not much different than that. Okay? Just bent a little different. That's all. That's it. That's your serving, your common sense serving for the day. Now we take a look at some old problems such as this one, where we would take regions such as this and we were revolving it around the x-axis, for example, and creating solids, and we found the volume by slicing it up into many pieces this way. In fact, we sliced up the entire region into small little rectangles, and then we consider the idea of what would happen if you take a little rectangle and spin it around. And of course we would get a shape more or less like this, and that's called a disk. So today we consider something else. What would happen if you take this and you spin it, just give it a little spin this way, and instead do rectangles this way, and you spin it around? Well, you would get something different. And in fact, there's nothing special about the other shape, this one or this one. There's nothing special about them. You could really, your imagination is the only limit. If you wanted to, you could cut them up into little stars and make the solid here and then spin it around and then find that area, and then you could almost make a cutout out of that region and say, hey, that part I've taken care of, and then make another little star, or make a tooth, or whatever, make a Pac-Man. You could cut up the region however you want. Your imagination is the only limit. As long as you spin it around and find that volume, put it aside, and then do the next one. It's just that these rectangles make it provide an organized way of doing it. So what we consider today is the rectangles. So a couple of things I gotta say. There's nothing special about these shapes. Your imagination is the only limit. What we consider today is we imagine this type of shape, cutting it up this way and revolving it around this way, and see what you would get. You'd get something like this, which of course would be has the same topological shape. Inside here is hollow. It's the same as this shape, except it's turned sideways. So, and that is of course the same shape as that, so long as I cut it here along the green line. If I cut it here, cut it here, and open it up, it would have the same effect as cutting this one and open it up. So really you have a quote-unquote box. And so then let's find the volume here. Let's go wide here. The little volume would be equal to the base times the height times the width. After all, if I cut it here and I open it, it is a box. But of course the base would be 2 pi r. And I'm going to make my radius here. The radius would be from here to here. That's my radius from the axis where I'm rotating it. We're going with y is equal, y is equal to 0. That's the axis that we're using to rotate it. And so this would be the radius. And let me continue here. Times the height times the width. Whew. I say salute to that. Shake it but not stirred. If you don't know what shaken but not stirred means, you gotta work on your swagger skills. That's from the Swagger Master, Agent 007. Alright. You guys have no idea what's in that water. Oops, it's not water. Anyways, so we continue with this. It shouldn't be that bad. It's just 2 pi. I'm going to leave some room here for my r. I'm going to erase this part. That was poorly planned. The r, and then I'll leave some room for the h. And then I'll do the width right now. Look at the width. This is how wide it is. This is how wide. It's hollow inside. It's just almost like a piece of carton once you open it up. That's a thin, really short box, quote-unquote box. The thinness is this much. This would be the height. If you open it up and put it on the floor, this is how tall it is. That's the width of it. So I would call that a dy. Whoops. I would call that a dy over here. All right, let's work on the r. Got to put your fingers on it. R is from here to here. So maybe from here to here. Same thing as from here to here. This is my r. So it's y1 and y2. I'm going to go with y2 minus y1 since it's always top minus the bottom. y2 minus y1. How about the height? The height would be this. Of course this one, the height was standing up, but this one the height is laying down, so that shouldn't be a problem for you. We'll still call it height. It's this difference of x's. So this one is called, let me see, I'm going to go with blue here. This one is, and this one, so this one I'll call, this one's x equals 16, so I'll call this x3. This one, of course, I already called this y2, so I gotta call this, I'm gonna go with x2 just to keep it consistent, x2. Okay, so then this would be right minus left, x3 minus x2. x3 minus x2. And then I go on and continue to clean this up. 2 pi. Okay, I scan through this, scan it. I'm looking at my differential. That one, dy, tells me something. It tells me something really important. It tells me all here, if there's a y there, okay, I'll leave it. But if there's an x, I gotta exchange it for y's. I only want y's or constants here. Y's or constants, because I'm doing it with respect to y. I don't want to see any x's. If there's x's, I'll exchange them. Either they may be constants or I'll exchange them using the exchange rate here. So let's do it. So y2, let me think, y2 was right here. That just stays as y. I don't need to exchange it. It's a generic one, it's changing, so I just leave it as y. y1, where was y1? Oh, this was y1 right here. That was 0. x3, where's x3? x3 was this one. Is that a constant? Yes, it is. 16, so I leave it. x2 was not a constant, it's changing, so I gotta exchange it for y's. I'll do that in the next step. X, and then I'll call this x2 so you don't forget. It comes from this relationship right here. This whole curve I'm calling x2, x and y2 curve. And then I have a dy, and then I continue here to take small steps. 2 pi y 16 minus x. Alright, it's time to do the exchange here. X here would be equal to a y square times dy. And then I got dv is equal to 2 pi times 16y minus y to the third times dy. So I took this y and I distributed it, 16y, y to the third. Now I do my favorite step. The steps that always adds a little swagger to my life. The deep S. And then I observe the differential of y would tell me I need y limits here. So I consider all these little rectangles that I had. They started here. They go all the way. They start here at y is equal to 0 and they stop here at y is equal to 4. Well, because x went to 16, square root of 16 is 4. So my limits should be from 0 to 4. And then you could do, this part is kind of easy. This would be equal to 2 pi, I'll leave that outside, and this would be 16 y squared over 2 minus y to the third over 3, and I'm going from 4 to 0. And that part is kind of boring. You just plug in the 4, and then calculate whatever you get, and then you plug in the 0, and then whatever you get, you subtract them. And that's it. In case you're keeping track, I think we can... Let me see. I think we got that here somewhere. 16 integrate 16y minus y to the third. That would be equal to 128 pi. I just calculated that in my head. 128 pi. Take that. Okay, salute. Alright, let's try another example just for fun. This cone, right? The volume of the cone. Last time we did it by spinning this triangle around the y-axis, and we spun it one little region at a time, one little rectangle. And every time we spun one of these little rectangles, we would get a shape, a little differential shape, such as that one as a disc. So today we consider a different option. What if you spin regions this way? Not this way, but this way. We would get regions. By the way, if you ever have trouble spinning these regions around, I have them cooked up already, but I probably should just show you one idea that you can always use. You take that one, you copy it, and then you put another piece of it over here, more or less the same distance from the axis where you're rotating. You go the same distance left and right, and then you just join them. You just join them carefully with little circles on the top. You see? Anybody can do this, right? That would be one way to help you make the drawings in case you want to. But I had already cooked this one that's a little transparent, so you can see a little bit behind it. I'll show you how to do the transparency later. I'm just kidding. Alright, anyways, we find the volume here. I want to find the volume here. So I'm going to go with the dV. Well, again, I can imagine cutting this thing up. Cutting it up right here. I cut it and I open it. And if I do that, it's no different than our initial lesson here with common sense. It's just like this being opened up. So it's a box. It has the same topological shape as a box. So the little volume would of course be, as all boxes, base times height times width. And then I just go on and slowly, methodically, I substitute each one of them. The base, that's all the way around. That would be the circumference. 2 pi r for the appropriate r. The r would be the distance from here to there. That's r. Okay. The height, that would be this distance. Height would be from here. Height all the way to here. I should put it over there. And then the width, let's look at the width. So this would be height, the width. What is the width? The width is this piece right here. Look at my fingers. Power of the fingers right there. That's the width. It's this little tiny width. That's how tall the box would stand if I opened it and laid it down on the surface. And that width is a distance this way, so it would be a dx. Duh. Alright, so then I go on and I substitute everything. Notice how we do this all with common sense, almost nothing to memorize. It's brilliant. That's why I'm starting to love this chapter a lot. This is officially my favorite chapter. I'm just kidding, they're all my favorite chapter. Like my son, every time he hears a song, Putty, Putty, is that your favorite song? It's my favorite song. Every song is his favorite song. So what do we calculate here? 2 pi r. I'm going to leave some space for my r here. leave some space for my h here. Look how easy this is. I can't believe I get paid to do this. R, put your fingers on it. This is R. R. Horizontal or vertical distance. This would be a horizontal distance. Therefore, difference of x's. If it was a vertical distance like this, difference of y's, horizontal difference of x's. Difference of y's, difference of x's, difference of y's, difference of x's. What are they? I'm going to call this one, this is one of my x's, and I'm going to call this one another one of my x's. Yeah, so this one I'll call x2, I'll call this one x1. Okay? So then the radius would be x1 minus x2. How about the height? Got to put your fingers on it. Here's the height. Difference of y's or difference of x's? Difference of y's. So since I already called this 1, I'm going to keep it consistent. This is y1, and all this is governed by this relationship, x1 and y1. Okay, if I want to exchange, I got to use this exchange rate here. And of course, I'll call this one y3. So therefore, I take my fingers, I look at the height, top minus the bottom. So it's y1 minus y3. Capiche? Top minus the bottom. Then I observe my differential. What kind of differential have I got? I got x's, differential of x's. So I want to translate everything here. I only want constants or x's. Okay, constants or x's. That's all I want. I don't want to see y's or v's or t's or anything that's not a constant or an x. So that way I know, that's what tells me which things I got to replace and which things I got to leave alone. So x1, I go to my picture here, x1, x is 1. Since I'm doing differentials, I'll leave it. I'll leave the x there. x1 is no problem. Minus x2. x2 is a constant, so that's 0. y2. Where's my y2? That's actually a y. Where'd that come from? That came from the height. That's actually a y1. It would help if I write it better. So y1, I don't like that y1 because I have to exchange it. My differential is x, but I'll leave that for the next step. y1. y3 is equal to 0, so I'm good with that one. So it's almost looking good. Look at that. I only have constants or x's except for that guy right there, y1. So I go to my x1, y1 relationship and I exchange it. I need to exchange that y for x's, and so it's already solved here. So I'll just substitute it here. 2 pi x times y1. That would be negative 10 over 4. I hope you don't mind. I'm going to write negative 5 over 2. X plus 10 dx. And I don't have to write the minus 0. And now I'm good. My differential of v would be equal to 2 pi. I don't have to do this, but I distribute the x in there because when I integrate, the 2 pi will come out. That's why I do this. Negative 2 x squared plus 10x dx. Isn't that nice? So, what's next? Slap the super S on both sides. Observe the differential so you can pick up the right limits. X. So my x's, I need my x's, they go from 0 to 4. If you don't know that, you would intersect these two lines. Y equals 0 and y equals that. So it goes from 0 to 4, and then it just becomes a really trivial problem. Super easy one. You can do that if you need to practice. If you don't need to practice, if you're way too sexy for the practice, then you use some computer or algebra or whatever. Okay. Let me see if I have that one. I think I did that one. You just want to see what I do? Maybe I should show you. So I integrated that one. Let me see. That would be 2 pi times integrate 5 halves squared plus 10x going from 0 to 4. So this is Mathematica. This is like Wolfram. And of course the answer is an expected result 160 over 3 pi. I'll let you check that. Nice, huh? Want to see one more? Let's see. Try this one. We got a little funky curve here going bounded by the y-axis. Y squared equals 6x squared. Y equals 4. Those are the boundaries. and we're spinning it around, I don't know, say we're spinning it around x equals 3. And we're probably going to need the point where these intersect. So you set these two equal to each other. Y is equal to 4. Y is equal to 4, and y is equal to that. So you substitute the 4 in here. That would give you, just do it right here, 4 squared is equal to 6x. So x is equal to 16 over 6. That's the point here. This is x equals 16 over 6. Okay? Can you see that? Let's move it up. All right, whatever. So now let's start doing some spinning here. So we cut up in the regions like this, and we spin them around. Again, if it helps you, just spin, you know, one little region at a time, and then fill in the gaps, and that should help you picture it. That's what we call a shell. They're called shells because they could be. It's like the bullet. You know, if you take the bullet out, there's a shell left in there. It's like a hollow cylinder. And you can imagine a whole bunch of them stacked inside each other, like Russian dolls. Anyways, we find the volume here. Little volume. What would the little volume be? Well, again, this shape is no different than the other ones we've been doing. They're all shaped. Topologically, they're shaped like this. And if you cut that and open it up, it looks like a box. So this one's no different. The volume would be base times height times the width. And I start working on the base would be 2 pi r. The height would be the width would be this much, which would be a dx. Then I go on and I leave some empty space here for my r and my h. And I put my fingers on the r. This would be the radius from here to here. R goes from here to here. This point right here on the curve, I'll call it x1, and I'll call this one x2. So then the radius would be from here to here. So the radius would be right minus the left, x2 minus x1. The height would be difference of y. So I call this one y3, and I call this one, I gotta call it x1 to keep, no. I gotta call it y1 to keep it consistent, and I'll circle this. This is my x1, y1, and the relationship between them, in case I gotta exchange. Where was I? So, what? R was equal to x2 minus x1, and then the height I put my fingers on it, top minus the bottom, so it'd be y3 minus y1. And the rest of it is kind of easy. Then, alright, next step is I scan through this, scan through it. Look at my differential as dx, so I only want x's or constants. Let's look at x2. Is x2 a constant? Yeah, x2 is a constant. X was equal to 3, and this was x2, so that's 3 minus x1. Is x1 a constant? No, x1 is changing. What's up, buddy?
Where's the charger with your iPad?
Really, dude? Alright, so we were computing the x2 minus x1. X2 minus x1, check. Now I need a y3 minus y1. Y3 minus y1. Right here. The y3 is a constant. Anything that's a constant, I put it on there. Constant is 4 minus y1. Oh, this y1 is not a constant. It's changing all over the place. So I just leave it as y1. And I consider that a good step in the right direction. 3, it's almost there except for that y. I'm about to replace that y. And I can leave the 1 out of it because there's only one x left there. y1, alright, I gotta exchange it. So I gotta use my exchange here. Y, let me think. The y square is equal to that, so therefore y is equal to the square root of 6x. So y would be equal to the square root of 6x. And that would be times a dx. And then what happens? Then your dv is equal to 2 pi. I gotta do a little fall here. 12 minus 3 square root of 6x minus 4x plus x times 6, or sorry, x times x times the square root of 6x, all that times dx. Right? Move it slightly over so you can see it. And then that's looking a lot better. I know it might look scary, but really this is a basic one, basic integral. dv would be equal to 2 pi times 12 minus, let me think, this would be 3 times the square root of 6 times x to the 1/2. That's if you split this into two pieces. And I put it here on purpose, x to the 1/2, because when I integrate, this will be easy to integrate. All I do is add 1 to the exponent and divide by the new exponent. Minus 4x, this would be plus, what is that? Square root of 6 times, how many x's have I got? 3/2 times dx, right? Again, let me see if I can move this over so you can see it, the whole piece. And after that, what's the next step? After that, we slap the sum on both sides, and we carry that limit. Observe the differentiating, and the differential is x. So I want x limits. X are going from where to where? They're going from here to here. I got a bunch of these little shells nested inside of each other, and I count them all, starting here at 16 over 6. That's where these two lines meet, 16 over 6, and I go all the way to 0. 0 to 16 over 6, and then the rest of that is pretty boring. So I'll let you do that if you want. Okay, that's example number 3. This other example I won't do, but I just want to point out something that is really important here. If I was to do this with just imagine doing this with horizontal shapes. Suppose I cut it up into pieces like this. You know what's going to happen is that's going to be fine and dandy when I go up here, but here the limits would change. Well, so for these ones over here, okay, think about what would the limits be here from here. You could call this x1 and you call this x2, and for these ones it would be x2 minus x1, but all that would change the minute you start going over here into this territory. For these ones over here, it would be, you'd have to call this x3 and x2. This would be x3 minus x2. And so if you were doing discs, okay, this means spinning it, or washers in that case, spinning it this way. If you were doing washers, you would have to break it up into two separate integrals, starting right here. For the ones above here, the limit would be this minus this, and for the ones down here, it would be this minus this, which are different x's. It's a long way of saying that if you were doing the disc method here, if you were cutting up into pieces that are horizontal, you would have to need you would need two separate integrals to cut up into infinite pieces. They'd have different limits. Consider the alternative, what we just learned today. This is why this is an important one to talk about. If you go with pieces this way, throughout the entire region, the top would be y1, which would be this curve, and the bottom would be y2, which would be this curve. And that remains true no matter which part of the region you're in throughout the whole thing. What does that mean? If you do washers on this one, if you cut up into pieces this way, you can do it all in one integral. As opposed to if you cut it up this way, you need two integrals. Okay, that's why this is a nice thing to consider. It's similar to the same dilemma we had for areas. Some areas, depending on which way you cut it, you could do it all in one integral. If you cut it up with horizontal or vertical, you get one integral. If you cut it up the other way, you would need two integrals, or sometimes even more. So that's an important thing to note when you're choosing whether to cut things up this way or this into rectangles this way or rectangles that way. You might want to consider one or two integrals. You know how many integrals you're going to get. And if you like the workout, you might choose the one with two integrals just for the workout, if you're up for it. Alright, another topic for today here is often placed, I do this more out of tradition. So books will often have a region here on the XY plane, and they'll tell you the cross sections, but they'll spice it up a little bit. We've done cross sections that are shells, we've done them that are discs, we've done cross sections that are washers. So they spice it up here and say, what if you had a different kind of cross section? What if the bottom region looked like that, and at every single spot right here, when you take a cross section, the cross section is a rectangle where the width is twice the height. meaning you have many of these, and so you have some three-dimensional shape that looks more or less like this. They ask you find the volume. Well, the concept, if you understood the concept before, you shouldn't need any formulas. Anything, all you need is really common sense. And so you say, all right, I'm going to find each one of those cross sections one little volume at a time. And so these, in this case, they are boxes. So the volume would be base times height times width. And the base would be, well, you have to look at the bottom on the XY plane here. The base would be this much. It would be y1. I'm going to go with y1 is over here. That's this line. And this would be y2. So the distance from here to here, that's the base. So it would be y1 minus y2, the height. Oh, they tell us something about the width is always equal to two of these widths make one of the lengths. So the width would be equal to half the length here. So it'd be half of another y1 minus y2, right? And then the thickness would be, in this case, just a dx. And so your little volume would be 1/2 y1 minus y2 times y1 minus y2 times dx, and then you go on and substitute everything. What is y1? y1, or look at the differential dx. So that tells you what you want to keep and what you want to exchange. I keep all constants and all x's, and I exchange everything else. So the y1, I exchange it for 3x. y2 is a constant, y2 is 0. y1 again is 3x, y2 is still a constant, so it's dx. So my little volume here would be 1/2 times 9x squared times dx. That's it. Nice, huh? Then they would usually give you some limits, as they do here, from 0 to 5. And the rest of that is boring. 9/2 times x to the 3 over 3, going from 5 to 0. Whatever. Standard problems, they always ask you. And they don't have to be, see, again, the only limit here is your imagination. They don't have to be rectangles where the wide is two of these make one of these. They could be 3 of these make one of those, or 4 of those make. They could have all sorts of proportions. They don't even have to be rectangles. They could be triangles. You know, who says they don't have? They can't be triangles. They could have a whole bunch of triangles. The cross sections are triangles or semicircles. Why not? Like this one. What could you find the shape, the volume of a shape like that, where the cross sections are semicircles? It's just common sense. All you do is find one little volume. For a little volume for a shape like that, it would be the area times the height. The cross-section area times the height, or times the width. Yeah, let me see. Call it width. This consistent area times however wide this is. The area, the y would be a dx in this case. How about the area? Well, the area of a circle would be pi r square, but this is no circle, this is half of one, so I cut that in half, times dx. So my little volume would be pi over 2 times the radius squared times dx. Now all I have to do is use my common sense to figure out the radius. From here to here, that distance is y1 minus y2, right? The radius would be half, that would be the diameter. So therefore, the radius would be half that. So it would be y1 plus, y1 minus y2, top minus the bottom, divided by 2. That would cut it in half. That would be the radius squared dx. I observe my differential x's, and I determine that I want only x's and constants here. So I exchange whatever needs to be exchanged. y1 was 3x. y2 was equal to 0 all over 2, and that's squared times dx. And then the rest of that is pretty boring.